Welcome to this video on error control. In data communication, errors are unavoidable. Bits may get flipped, frames may be lost, or signals may get distorted during transmission. That is where error control plays a vital role. Error control is a set of techniques and protocols that ensure data is delivered accurately and reliably from sender to receiver. It not only detects error in transmission but also provides ways to correct them through retransmission. In data communication, errors can occur due to noise, interference, or signal distortion. Error control ensures reliable data transfer between sender and receiver by detecting and correcting these errors. Error control techniques are mainly divided into two categories: stop and wait ARQ and sliding window ARQ. Under this sliding window method, we have two important types: go back N ARQ and selective reject ARQ. Each method plays a vital role in ensuring accuracy, efficiency, and reliability in data transmission. Stop and wait ARQ is an extension of stop and wait flow control designed to handle retransmission of data in case of any frame is lost or damaged during transmission. To make retransmission possible, four key features are added. First, the sending device keeps track of the lost frame. It is transmitted until it receives an acknowledgement for that frame. By keeping a copy, the sender can retransmit any lost or corrupted frame until it is successfully received. Second, for identification, both data and acknowledgement frames are numbered alternately 0 and 1. Third, if the receiver detects an error in the data frame, it sends back a negative acknowledgement. When a negative acknowledgement is received, the sender retransmits the frame sent after the last successful acknowledgement, regardless of its number. And finally, the sending device uses a timer. If an expected acknowledgement does not arrive within a specific time limit, the sender assumes the frame was lost in transit and send it again. If a frame is detected by the receiver as an error, it returns a negative acknowledgement frame and the sender retransmits the lost frame. Let us take, for example, a sender that transmits a data frame and one of them is found to be an error. Sender transmits data frame 0 and receives acknowledgement 1, indicating it expecting data 1. Now sends data 1 and receiving acknowledgement 0. Sender now transmits the next frame data 0. Receiver discovers an error in it and returns negative acknowledgement. Sender retransmits data 0 again and receives acknowledgement 1. Let us look at the limitation of stop and wait ARQ. In the stop and wait method, at any point in time, there is only one frame being sent and waiting for acknowledgement. This approach leads to poor utilization of the transmission medium since most of the time the channel remains idle while waiting for an acknowledgement. To improve efficiency, it is better to have multiple frames in transit simultaneously even while waiting for acknowledgements. This idea forms the basis of two advanced protocols: go back in ARQ, selective repeat ARQ. These methods overcome the limitation of stop and wait by allowing multiple frames to be sent before acknowledgements are received. In go back in ARQ, if a frame is lost or damaged, the sender retransmits all frames that were sent after the last acknowledged frame. This means that even if only one frame is corrupted, multiple frames may need to be resent, ensuring that the sequence of data remains correct. Similarly, if an acknowledgement is lost, the sliding window mechanism waits for a specific timeout period. If the acknowledgement does not arrive within that time, the sender assumes a problem and retransmits the data frames again. This method ensures reliability through it can sometimes result in redundant transmission when only a single frame or acknowledgement is lost. In selective reject ARQ, also known as selective repeat ARQ, only the specific frame that was damaged or lost during transmission is retransmitted. When a frame is found to be corrupted in transmit, the receiver sends back a negative acknowledgement for that particular frame. The sender then resends only that frame even if it is out of sequence with the others. This means the receiving device must be capable of reordering frames, placing each transmitted frame in its correct position. This approach makes the data transmission more efficient by avoiding unnecessary retransmission of frames that were already received correctly. Let us understand how selective repeat ARQ works with an example. The sender transmits 6 data frames numbered 0 to 5. When frames 0 and 1 arrive safely, they are not immediately acknowledged. Next, frame 2 is found to be damaged in transit. So, the receiver sends back a negative acknowledgement. This negative acknowledgement indicates that the earlier frames 0 and 1 were received correctly, but the frame 2 needs to be retransmitted. Unlike go back in ARQ, the receiver doesn't ask the sender to resend all the following frames. Instead, it simply records only the damaged frame. Meanwhile, the receiver continues accepting frames 3, 4, and 5 even while waiting for the new copy of the frame 2. Once the frame 2 arrives correctly, the receiver sends an acknowledgement file confirming successful receiving of the new frame 2 along with the original frames 3, 4, and 5. To handle this, the receiver must have the logic to reorder frames, keeping track of which frames are missing and which ones have already been acknowledged. This makes selective repeat ARQ both efficient and reliable in managing retransmission errors. Let us compare go back in ARQ and selective reject ARQ. At first glance, retransmitting only the specific damaged frame as done in selective reject ARQ may seem more efficient than resending all frames after an error like in go back in ARQ. However, selective reject ARQ requires greater complexity. The receiver must have enough memory to store and reorder the frames, while the sender needs extra logic to identify and resend only specific frames. This makes the system more expensive and harder to implement. Although selective reject ARQ offers better performance in theory, in real world applications it is rarely used. Most systems prefer go back in ARQ as it provides good balance between efficiency and simplicity of implementation.